Good day, classmates, and to our professor, Dr. Angeles. I am Mr. Ron Alfie Huson, and I'll be explaining the topic certain probability distributions, focusing on the common types of distributions in mathematical statistics. This presentation is only limited to the definition, introduction, basic concepts, and some examples of each type since there are assigned reporters to elaborate each. So probability distributions are a core concept in mathematical statistics, helping model and understand random processes. Probability distributions are tools in statistics that help understand how likely different outcomes are in a random situation. Think of it like a way to describe all the possible results of an event and how likely each one is to happen. For example, if you roll a die, a probability distribution can tell you that each number, 1 to 6, has an equal chance of coming up. They help us predict and analyze patterns in random processes. So what are the different types of probability distributions? So the different types of probability distributions are Bernoulli distribution, binomial distribution, Poisson distribution, geometric distribution, normal distribution, and exponential distribution. Let us discuss the Bernoulli distribution. The Bernoulli distribution models a random variable with two possible outcomes, typically labeled as 1 success and 0 failure. The probability of success is P, and the probability of failure is 1 minus P. And it follows this function. The probability of x equals x here could be 1 or 0, is equal to the piecewise function P if x equals 1, and 1 minus P if x equals 0. The Bernoulli distribution is fundamental in probability theory because it models binary outcomes, where each trial has only two possible outcomes, either success or failure. What are some examples of Bernoulli distribution in real life? So the first example is a coin flip or a coin toss. So for flipping a fair coin, the possible outcomes are heads, which is success, or tails, which is failure, where the probability of heads, which is success, is P, and that is P is equal to 0.5 or 1/2. Another example of Bernoulli distribution is the pass or fail in a test. So when a student takes a pass or fail test, the outcomes are passing the test, which is success, or failing the test, which is failure, where the probability of passing is P and the probability of failing is 1 minus P. Another example is in manufacturing quality control. So isn't it that in a production line, each product can either be defective or non-defective? The possible outcome is either a product passes quality control, which is success, or it is defective or does not pass the quality control, which is failure, with the probability of P or probability P of being non-defective. Another example is in drug efficacy in clinical trial. So when a drug is administered to a patient during a clinical trial, the possible outcome is either the patient responds positively to the drug, which is success, or does not positively respond to the drug, which is failure, with probability P representing the effectiveness of the drug. Let's take a look at the other examples. Another is in sports match, especially if it's a win or lose. So when a football team plays a match, for instance, the team wins, or that is success, or loses, or that is failure, where P is the probability of the team winning based on factors like team performance and opposition strength. Another is in a survey response, specifically if it is a yes or no question. When a survey asks a respondent a yes or no question, the respondent answers yes, which is success, or no, which is failure, where P is the probability of a yes response. Another is in voting behavior in an election. So when a voter is asked if they will vote a particular candidate, the voter either votes for the candidate, which is success, or does not vote for the candidate, which is failure, with probability P indicating the voter's likelihood of support. Now let's deal with problems that involve computations. Let's have the example. First example, in a factory, each product produced is either defective or non-defective. The probability that any given product is defective is 0.02. If X equals 1 represent a defective product, find the probability of X equals 1 and the probability of X equals 0. So first, let's get the given. So we know that P is equal to 0.02. That is the success. So therefore, it's easy to get the probability of X equals 1. The probability of X equals 1 will be 0.02 also. And now, let's get the probability of X equals 0 or non-defective. We will use the formula 1 minus P. Since P is already given, which is 0.02, we just substitute that in our formula. The probability of X equals 0 is now equal to 1 minus 0.02. Simplifying this, the probability of X equals 0 will be 0.98. Let's have another example. Suppose a new vaccine has a 95% success rate, meaning that 95% of vaccinated individuals become immune to the disease. Let X equals 1 be the event that an individual becomes immune to the disease. So first, let's write the value of P. The value of P in this case is 0.95. Since P is equal to 0.95, we can say that the probability of X equals 1 is also 0.95. Now, let's get the probability of X equals 0 using the formula 1 minus P. Since P is already given, so we just substitute 0.95 in place of P. So there we have 1 minus 0.95. And 1 minus 0.95 is equal to 0.05. So the probability of X equals 0 equals 0.05. Now, what are the limitations of the Bernoulli distribution? The Bernoulli distribution only applies to binary outcomes. So it's not suitable for modeling multi-outcome events or continuous data. The Bernoulli distribution is a way to model situations where there are only two possible outcomes, often called success and failure. For example, flipping a coin can result in either head or success or tails or the failure. However, if you have an event where there are more than two outcomes, like for example, in rolling a 6-sided die, which can land on 1, 2, 3, 4, 5, or 6, the Bernoulli distribution isn't suitable because it can only handle those two outcomes. So similarly, if it does not work for continuous data, like for example, when you are measuring height or time, where values can vary infinitely within a range. So now let's proceed to the second type, which is the binomial distribution. The binomial distribution describes the number of successes in n independent Bernoulli trials, where each trial has the same probability of success P. The probability mass function, PMF, is the probability of X equals K equals n chosen K times P sub K times quantity 1 minus P raised to n minus K, where K is equal to 0, 1, 2, and so on and so forth. By the way, when we say probability mass function, A probability mass function, or PMF, is a function that describes the probabilities of discrete outcomes in a random variable, and it tells you how likely each possible value is. So let me provide some real-life examples and computations about binomial distribution. So let's have this problem. You flip a fair coin 10 times. What is the probability of getting exactly 4 heads? So here we need to find the values of n, p, and k. So let's write the given. Here, n is equal to 10 since you need to flip the coin 10 times. P is equal to 1/2. Why? Because the probability of getting a head in tossing a coin is 1/2 or 0.5. You're asked to find the probability of getting exactly 4 heads. So therefore, k is equal to 4. So we substitute that in our probability mass function. By substitution, we have the probability of x equals 4 equals 10 chosen 4. So here you need to simplify this using the combination formula times 1/2 to the 4th power minus times quantity 1 minus 1/2 raised to 10 minus 4. So that will be, so simplifying this using combination, that is 210. 1 minus 1/2 is also 1/2. Further simplifying this, we now have the probability of x equals 4 equals 210 times 1 all over 1024. So that is equal to 105 all over 512 in lowest terms, or that is equivalent to 0.20507. So that is the probability of getting exactly 4 heads in flipping a coin 10 times. Let's take another example. A student guesses on 5 multiple choice questions, where each question has 4 choices and only one is correct. What is the probability that the student gets exactly 3 questions right? So again, we need to find the values of n, p, and k. What is the value of n in this case? If your answer is 5, you are correct. N is equal to 5 since the student must guess on 5 multiple choice questions. How about the value of p? The value of p now is 1/4. Why? Because the probability of getting a correct answer in a multiple choice question with 4 choices is 1/4. And what is the value of k? Ayan. So the correct answer is 3. Since we already obtained the values of n, p, and k, we need to substitute that in our probability mass function. So by substitution, the probability of x equals 3 equals 5 chosen 3 times 1/4 raised to the 3rd power times quantity 1 minus 1/4 raised to 5 minus 3. So we will simplify this one using combination. So that will be 10. And then 1 minus 1/4 is 3/4. Now let's simplify this part. That would be equal to 10 times 9 all over 1024. Now multiplying these fractions, that would give us 45 all over 512 in lowest terms, or in decimals, that is 0.08789. So that is the probability that the student gets exactly 3 questions right. So these are examples of the binomial distribution. What are the limitations of the binomial distribution? The binomial distribution assumes independence between trials and a fixed probability of success, which may not hold in real life. The binomial distribution assumes that the outcome of one trial does not affect the outcome of another. For example, if you flip a coin, the result of one flip should not change the chances of the next flip. But in real life, this might not be always true. For instance, if you're testing a new drug, the response of one patient might influence another's response. Now, let's proceed to the third type, which is the Poisson distribution. What is the Poisson distribution? The Poisson distribution models the number of events occurring in a fixed interval of time or space, assuming that events happen independently and at a constant average rate. This is lambda. Okay, the PMF is, or the probability mass function is, the probability of x equals k equals lambda raised to k times e raised to negative lambda all over k factorial, where k equals 0, 1, 2, 3, and 4. So let's have an example. An example of a real-life situation where the Poisson distribution is evident is this. The number of emails a person receives in an hour, given that the average rate is 10 emails per hour. So, what is the reason why is it considered under Poisson distribution? So, here is why the situation fits the Poisson distribution. Number one is because it is an example of a discrete event. The number of emails received is a countable quantity. So, you can receive 0, 1, 2, 3, and so on emails in an hour. Another is because it involves a fixed interval. So, the time frame here is fixed, which is 1 hour. So, Poisson distribution is often used to model events in a fixed intervals of time or space. Another is the presence of the average rate. So, the average rate of receiving emails is known, which is 10 emails per hour. This average is referred to as the parameter lambda in the Poisson distribution, which represents the expected number of occurrences in that particular interval. Another is because of independence. So, the occurrence of emails is generally independent of each other. One email coming in does not affect the likelihood of another email arriving. So, let's now have some examples that involve computation. Suppose a call center receives on average 3 calls per minute. What is the probability that the center receives exactly 5 calls in a given minute? So here we need to find the value of the lambda and the value of k. So in this case, lambda is equal to 3. And the value of k is equal to 5 since we are asked to find the probability that the center receive exactly 5 calls in a minute. So let us follow the probability mass function. By substitution, this would be equal to probability of x equals 5 equals 3 to the 5th power times e raised to negative 3, okay, all over 5 factorial. So therefore, that's equal to 243 times this decimal all over 120. So simplifying this, we now have the answer as approximately equal to 0.1008. So that is the probability that a certain center receives exactly 5 calls in a given minute. So let's have another example of a real-life situation that involves the Poisson distribution. So an intersection has an average of 1.5 accidents per month. What is the probability that there will be no accidents at the intersection in the given month? So again, we need to find the value of the lambda and k. So in this example, lambda is equal to 1.5 and the value of k equals 0 since we are asked to find the probability that there will be no accidents. So let us write our probability mass function and let's substitute the following values into our formula or function. So we have the probability of x equals 0 equals 1.5 raised to 0 times e raised to negative 1.5 all over 0 factorial. So simplifying that would be equal to, since this is 1 and this is also 1, so we are left with e raised to negative 1.5. So using our scientific calculator, we can simplify that, and our approximate value is 0.22313, and that is the probability that there will be no accidents at the intersection in that given month. Okay? So I hope that's clear to everyone. What are now the limitations of the Poisson distribution? So the Poisson distribution assumes that events are independent and occur at a constant rate, which may not be realistic for processes that change over time. So this type of distribution only assumes that events occur at a constant average rate over time. So there is a constant average rate over time. So in other words, if the average rate, for instance, is 10 emails per hour, the model assumes that this rate does not change. However, in reality, the rate of incoming emails might vary throughout the day. For example, someone might receive many more emails during work hours compared to late at night. So that's the limitation of this type of distribution. Now, we proceed to the fourth type, which is the geometric distribution. The geometric distribution models the number of trials needed to get the first success in repeated independent Bernoulli trials with probability P. And the probability mass function is the probability of x equals k equals quantity 1 minus p raised to k minus 1 times p, where k could be 1, 2, 3, 4, and so on and so forth. So to better understand the geometric distribution, let us have a concrete example, or a real-life example, rather. So the number of times you need to roll a die to get the first 6. So the scenario here, class, is an example of a geometric distribution. So the scenario of rolling a die until you get the first 6 can be modeled using geometric distribution. And here are some reasons why. Number one is that it is an example of discrete trial. Each roll of the die is a discrete trial. You either roll a 6 or success, or you don't roll a 6, which is failure. Another is that it has a fixed probability. The probability of success, or rolling a 6, remains constant for each trial. For a fair 6-sided die, the probability of rolling a 6 on any given roll is always 1 over 6. Another reason why it is a geometric distribution is because of its independence. Each roll of the die is independent of the others. The outcome of one roll does not affect the outcome of the next roll. Another is counting trials until the first success. So whenever the situation involves counting trials until the first success, that is considered geometric distribution. So this distribution specifically models the number of trials needed to achieve the first success. And in this case, if you are counting how many rolls it takes until you get your first 6, therefore indeed we say that this is an example of a geometric distribution. Now let me provide you with some real-life examples with computations. So you roll a fair 6-sided die. What is the probability that you roll a 3 for the first time on the 4th roll? So here we need to identify the values of P and K. So what is the value of P in this case? If your answer is 1/6, you are correct. Why 1/6? Because the probability of getting a 3 in rolling a single die is 1 over 6, since there is only 1 3 in the outcomes or in the sample space. And here, since we need to find the probability to roll a 3 for the first time on the 4th roll, this implies that our K must be equal to 4. Now, let us use our probability mass function. P or probability of x equals k equals quantity 1 minus p raised to k minus 1 times p. So, by substitution, we arrive at this. Clear? Next, let us simplify the expression here. So we now have the probability of x equals 4 equals 5 over 6 to the 3rd power times 1/6. So let's just simplify this expression. The probability of x equals 4 is now equal to 125 all over 216 times 1 over 6. Multiplying this, we arrive at 125 all over 1,296 in lowest terms, or that is approximately equal to 0.0964. So this is the probability that you will roll a 3 for the first time on the fourth roll. Let's have another example. A basketball player has a 70% chance of making a free throw. What is the probability that they make their first free throw on the fifth attempt? So again, let's determine the value of P and K. P here is 0.7 by converting 70% to decimal. And our K here is 5 since we are after the fifth attempt. The probability that they make the first free throw on the fifth attempt. So let's write our probability mass function. And then let's just substitute the following into our function or formula. So the probability of x equals p equals quantity 1 minus 0.7 raised to 5 minus 1 times 0.7. So simplifying this further, we now have 0.3 to the fourth power times 0.7. Thus, we arrive at this answer. Okay? So multiplying that, the probability is a very small. So that is 0.00567. So the probability that they make their first free throw on the fifth attempt is 0.00567. So let's have another example. Suppose a factory produces light bulbs and 1% of them are defective. What is the probability that the first defective light bulb is found on the 8th inspection? So let's get again the values of P and K. So what is our value of P here? If your answer is 0.01, you are correct by converting 1% to decimal. Here we are after the 8th inspection, so K is equal to 8. Let's write down our probability mass function and perform substitution of values. So we arrive at this. Now simplifying this further, we now have so we have the probability of x equals 8 equals 0.99 to the 7th power times 0.01. So simplifying that, we arrive at this, and then that's approximately equal to 0.009321. So the probability that the first defective light bulb is found on the 8th inspection is 0.009321. So napakaliit lang po ng probability. Now, what are the limitations, or what is the limitation of this probability distribution? So, geometric distribution, like the Bernoulli and binomial distributions, it assumes independence between trials and a constant probability of success, which may not always be applicable. So, the geometric distribution assumes that each trial or each roll of the die, for instance, is independent. So this means that the outcome of one roll does not influence the outcome of another. So in reality, this might not always hold true. For example, if a die is biased or if the rolling conditions change, the outcomes could become dependent or not independent. Now let's proceed to the fifth type, which is the normal distribution or the Gaussian distribution or the Gaussian distribution. So a continuous distribution widely used due to the central limit theorem. So I think you are still familiar with the central limit theorem, which states that the sum of independent and identically distributed random variables tend to follow a normal distribution. It's characterized by the mean. So this is the population mean and a variance in this symbol, which is the population variance. So let me provide you with an example of a situation that involves the normal distribution or Gaussian distribution. So this is an example. We have the heights of adults in a population where most people are near the average height and fewer people are much taller or shorter. So isn't it, if we're going to visualize this, it's like a bell-shaped curve, right? So this the example of adult heights in a population is a classic case of the Gaussian or the normal distribution. And here are the reasons why. Number one is because it follows a bell-shaped curve. So when you plot the heights of a large group of adults, you typically see a bell-shaped curve where most people cluster around the average height. The further you move away from the average, the fewer individuals you find. Another is because of the characteristic of the mean and the standard deviation. So in this scenario, the average height or the mean represents the center of the distribution. So the standard deviation indicates how much variation there is in heights. So a smaller standard deviation means most heights are close to the average, while a larger standard deviation indicates more variability or dispersion. Another is symmetry. So the distribution of heights is generally symmetric around the mean, meaning that the number of people who are shorter than average is roughly equal to the number who are taller. And furthermore, heights in a large population often fit this pattern. So it's actually a real world data. So that's why it's the most popular distribution, which is the normal distribution, because it's a real world data. So heights in a large population often fit this pattern, which is why the normal distribution is frequently used in studies related to human characteristics. Now, let me provide you with an example of a normal distribution with computation. Okay? So, assume that the heights of adult men are normally distributed with a mean height of 70 inches and a standard deviation of 3. What is the probability that a random selected man is between 67 and 73 inches? So, let's identify the population mean. The population mean is 70 inches. The standard deviation is 3. And our x sub 1 is 67. And x sub 2 is equal to 73. So here, we need to get first the z-score, which is given by the formula z is equal to the raw score x minus the population mean all over the standard deviation. So we get z sub 1 by using x sub 1 as the value of x, which is 67. So that is 67 minus 70 all over 3. So simplifying this, that's equal to negative 1. And then we get z sub 2 or the z-score if we will take this value 73 as the value of x. So 73 minus 70 all over 3, when simplified, that's equal to 1. So here we need to look at the respective values in the table of areas under the normal curve. So we are looking for the probability that z is in between z in between 1 and negative 1, or z is less than 1 but greater than negative 1. So by looking at the values of z in our table of areas of the normal curve, z value of negative 1 will give you 0.8413, and for 1 we have 0.1587. So if we're going to visualize that, we need to subtract the respective values, since we are looking for the shaded region in between them. So therefore, the probability is now equal to 0.86825, or that is 68.25%. Okay? What are the limitations of the normal distribution or the Gaussian distribution? So many real-world processes are not normally distributed. Specifically, when there are outliers, when we say outliers, these are the extreme values or skewness. So normality assumptions can lead to inaccurate conclusions in this case. So while many phenomena can be modeled using a normal distribution, there are numerous real-world scenarios that do not follow this pattern, particularly, for example, in the presence of outliers or skewness. So again, when we say outliers, an outlier is a data point that is significantly different from others in the data set. For instance, in income data, a few extremely high earners can skew the average income upward, making it less representative of the typical individual. If a data set with outliers is assumed to be normally distributed, it can lead to misleading conclusions, as the normal distribution assumes that data points are more evenly distributed around the mean. By the way, when we say skewness, it refers to the asymmetry of the distribution. If the data is skewed or not symmetric, in other words, or in simple words, it means that there are more values on one side of the mean than the other. For example, in the case of home prices, there may be a long tail of very expensive homes that skews the distribution to the right. So if you incorrectly assume this skewed data is normally distributed, you might misinterpret the mean and standard deviation, leading to incorrect insights and decisions. That's why, isn't it, in research, we have the parametric and non-parametric test. So one assumption of using parametric test is normality of data, but there are some data set where skewness and outliers are present, and in that sense, we need to utilize the non-parametric test. Okay, so now let's proceed to the exponential distribution, probably the last type of probability distributions that's under my report. So the exponential distribution models the time between independent events that occur at a constant rate, often used to model waiting times. Example, time between arrivals in a queue. And the cumulative distribution function is, so it's given by this formula, f of x equals the probability of x is less than or equal to x equals 1 minus e raised to negative lambda times x. Here, so it's not seen here, but x must be greater than or equal to 0. So the exponential distribution is commonly used to model the time between independent events that occur at a constant average rate. So this makes it particularly useful for scenarios like, for example, in waiting times, or the time until an event occurs, like the time between arrivals in a queue. So let's have some examples. Okay, so an example here, suppose a bus arrives at a bus stop every 15 minutes on average. So lambda equals 1 all over 15. What is the probability that the next bus will arrive in less than 10 minutes? So here, we need to use the cumulative function. So we have f of x equals the probability of x is less than or equal to x, which is equal to 1 minus e raised to negative lambda times x. So here, we are looking for the probability that the next bus will arrive in less than 10 minutes. So this must be 10. This must be replaced by 10. And then lambda will be replaced by 1 over 15 as stated in the problem. So by substitution, the probability of x is less than 10. So we will replace that into less than 10. Since that's indicated in the problem, we disregard the equal sign. So that's equal to 1 minus e raised to negative 1 over 15 times 10. So simplifying this, the correct answer now is 0.4866. So the probability that the next bus will arrive in less than 10 minutes is 0.4866, or approximately 48.66%. So what are now the limitations of the exponential distribution? The exponential distribution assumes that events occur at a constant rate lambda, which may not hold in real-world situations. For example, during peak hours in a call center, the rate of phone calls might increase, violating the assumption of a constant rate. So that's the limitation of using exponential distribution, no? It's difficult, no, to model or to say that all situations in real life follow a constant rate. Another is the presence of independence of events. So that's in addition to that. So the exponential distribution also assumes that events are independent of each other. In practice, events can influence each other. For example, if one customer calls, it might encourage others to call as well, specifically in situations like promotional campaigns or, for example, in emergencies. Another is memorylessness. So while the memoryless property is a feature of the exponential distribution, it may not reflect reality. In many cases, the time until the next event may be influenced by how long one has already been waiting, and that is actually true in real life. Another is because of there might be presence of non-exponential patterns in some situations. So many processes do not follow an exponential pattern but may follow other distributions such as the gamma or the gamma distribution, which can model varying rates or dependencies more effectively. I think gamma distribution will be discussed by the other reporters. So again, these are the different types of probability distributions. These are some of the different probability models or distributions in mathematical statistics, and understanding the various probability distributions is essential for effective modeling and analyzing real-world data. Each distribution here, be it normal, binomial, geometric, Poisson, or exponential, serves unique purposes based on the number of data and the assumptions we can reasonably make about it. So I have here a simple activity about identifying the type of probability distribution. So you may just pause the video and try to answer this one. Okay, so these are the answers for this activity. So you may pause the video and then you may try to answer the following. Yan. Okay, so thank you very much and God bless us all. Goodbye.